So here I've sketched out the myocardium, and we've noted that the myocardium is the contractile muscle layer of the heart, but this needs to be controlled, of course, and we've noted that it's controlled by external influences from outside, but it's also controlled internally. Now, just to orientate ourselves, what we have here is we have these would be the arterial valves just there, pointing up the way, so that would be aortic and the pulmonary arterial valves there. And also on this same plane we have the atrioventricular valve, so that would be the mitral valve or the bicuspid valve and the tricuspid valve on that side. So that's kind of where we are. Now, what there is in the heart is there are specialised autorhythmic fibres. Autorhythmic means that they are self-exciting because they are excitable cells. Now, when we say excitable in physiology, that's got a fairly specific meaning. So if we think about a cell here, this could be, let's say this is an individual myocyte, a myocardial cell. At rest, it's negative inside and positive outside electrically. There is a distribution of negative and positive ions, meaning there is an electrical potential difference across the cell membrane. Just as the same as you have a positive and a negative in a battery, you have a positive and a negative across the cell membranes of the individual cell. And in that state we say it's polarised. But then if it changes to being positive inside and negative outside, electrically speaking, we say it's depolarised. So that state is polarised, that state there is depolarised, this process is depolarisation. So these are specialised cells that are excitable. So an excitable cell is one which can generate an electrical potential across their cell membranes. And the only cells that do this are muscle cells and nerve cells. But of course the myocardium is made up of specialised cardiac muscle tissue. It's all muscle, the myocardium. Now, as we've said, autorhythmic means self-excitable. They are self-excitable tissues. And the first one we need to think about here is a crescent-shaped area of tissue. And as we see, this is in the right atrium. And this structure is often called the pacemaker, but it's correctly called the SA node or the sinoatrial node. So it's the sinoatrial node that generates the sinus rhythm. This is the sinoatrial node. It's a crescent-shaped area of tissue, as we see. It's 8 to 25 millimetres in length. It varies a fair bit between individuals. And it's in the right atrial wall. Now, it's actually inferior and lateral to the opening of the superior vena cava. So, as you might remember, the superior vena cava brings blood from above into the right atrium. The inferior vena cava brings blood from below into the right atrium. And this specialised area here, the sinoatrial node, it's in the atrial myocardial wall. It's inferior and lateral to the opening of the superior vena cava. If you looked in a heart actually inside, you can't see it. Well, sometimes you can in very old people, but in most people you can't see it from the inside because it's actually subepicardial. It's in the subepicardial area. So what you actually have round about the heart, you have an area called the epicardium round the outside and a layer called the endocardium inside. So the endocardial layer inside and the epicardial layer on the outside. And the sinoatrial node is subepicardial, it's just underneath. And it's made up of specialised myocytes. So in the fetus, when the myocardium is developing, 99% of the cells become contractile myocardial cells and fill up this area here, this area of the myocardium. They're contractile. But about 1% of the fetal cells differentiate into these autorhythmic fibres. Now, they're still part of the myocardium, but they're just specialised cells. So the cells here, for example, in the sinoatrial node, they're smaller and paler than contractile myocardium. So they are visible with good preparations under the microscope. So it's this sinoatrial node that generates new electrical impulses that are going to stimulate the contraction of the myocardium. Now, left to its own devices, it will generate new electrical nerve impulses about 100 times a minute. That's once every 0.6 seconds. But what actually happens is that's actually slowed down a little bit. So actually, in you at the moment, or any healthy person, connected to the heart, we have a sympathetic supply and a parasympathetic supply. So that would be the parasympathetic supply there, coming from the parasympathetic nervous system via the vagus nerve, and that would be the sympathetic nerve supply there. Now, when the sympathetic activity, that's going to increase the rate of depolarization. It's going to increase the rate, and the heart rate is going to increase. When there's parasympathetic stimulation, that's going to stimulate this sinoatrial node. But when the parasympathetic stimulates it with acetylcholine, that's going to slow it down. So normally there is parasympathetic stimulation that slows the heart rate down at rest to about 70 times per minute. And of course, it's fascinating, if a heart is taken out of the body in a heart transplant situation, then it carries on beating, even though these nervous system connections are taken away. Because this is autorhythmic, it will generate its own electrical impulses to cause contraction of the myocardium. So it's important to note that these connections of the autonomic nervous system, the parasympathetic and the sympathetic, they only modify the rate of this. It works fine without them. They're just modifiers for different circumstances. But this will carry on regardless on its own because it's autorhythmic. Now, once these electrical impulses have been generated, they actually propagate through the atrial myocardium. They actually are propagated along atrial myocardial muscle fibers to all parts of the atrial myocardium. Now, we did go through a phase of thinking there were specialised internodal tracts in this area, specialised conducting tissue, but we now know that this is not the case. The impulse just spreads and propagates through the atrial myocardium itself. And that's what causes the atrial myocardium to contract. So the electrical impulse is generated here. That reaches the action potential, which spreads electrically through the atrial myocardium. And when the wave of depolarization, this action potential, gets to an individual myocardial cell, in this case the atrial myocardium, what it does is it causes it to change from being polarized to being depolarized. That's the electrical change that is generated by these electrical signals. And when the myocardial cells depolarize, that's the message to contract. So the cell's just sitting there, polarized, not contracting. But then when it depolarizes, it knows it's time to contract, and that individual cell will contract. But of course, this is happening all over the atria, so we get atrial myocardial contraction. That's what increases the pressure in the atria. That pushes the blood through from the atria through to the ventricles. We get atrial myocardial contraction. But that's only the first part of the cardiac cycle. Of course, after this, we want ventricular myocardial contraction. So how is that coordinated? Well, this is the sinoatrial node. Sinoatrial node generating sinus rhythm. The sinus rhythm comes from the sinoatrial node. But then that's picked up by another node, which is just here, which is going to take the impulse from the atria through to the ventricles, from the atria through to the ventricles. So this node here that picks up this impulse, sometimes called a collecting node, is the atrioventricular node. So it's the atrioventricular node collecting the impulse which has been generated by the sinoatrial node, because it's connected to the atrial myocardium, and it collects that impulse. So the atrioventricular node is in the atrial component of the atrioventricular septum. So the atrioventricular septum is the atrioventricular septum. The septum is the bit that divides. So the septum is dividing the left heart, the body pump, from the right heart, the lung pump. It's the septum. So this is the atrial component of the septum here, dividing the atria, still made up of myocardium. And this is the ventricular component of the septum here, dividing the ventricles, still made up of myocardium, of course. So the atrioventricular node is in the atrial component of the atrioventricular septum. And from there, the impulse goes down in this cardiac septum, down to the ventricular part of the heart. And this is of immense importance because this bundle that we've drawn here, the atrioventricular bundle, taking the impulse down from the atria to the ventricles, that's the atrioventricular bundle there, formerly known as the bundle of His. Now this is so important because this is the only electrical conducting pathway between the atria above and the ventricles below. It's the only way the electricity can get through. It's the only way the action potential can get through. Because across the valvular plane just here, that plane there is insulating tissue. It does not conduct electricity. So the atria and the ventricles are separated by this insulating plane of tissue. The electrical impulses can't get through. So the valves don't transmit electricity. They're largely made up of collagen, which doesn't transmit electricity. And there's other fibrous tissue here, part of the fibrous skeleton of the heart, and that does not allow the transmission of electricity. So the impulse that gets to here, for example, to cause contraction of the atrial myocardium, it can't get through. This is insulating. This is insulating. It can't get through. The only way the electrical impulse can get through from the atria to the ventricles is through the atrioventricular bundle. Now, the atrioventricular node, before the impulse gets through to the atrioventricular bundle, has already slowed the impulse down. So it slows the impulse down a bit. And that's necessary because once the atrial myocardium is contracted, and as we know, that's going to generate the pressure in here that's going to send the blood from the atria through to the ventricles. But that process is going to take a little bit of time for the blood to move through. So we want to slow the impulse down so that when the impulse gets through to cause the ventricular myocardium to contract, these atria are full of blood. So we need a little bit of a pause for the blood to get from the atria through to the ventricles, to fill the ventricles up, to stretch the ventricles prior to ventricular systole. So the AV node slows it down, then it goes to this through the AV bundle, the only conducting part. There are disease processes, of course, where there's other conducting pathways, but that's pathological. So you might have heard a condition called Wolff-Parkinson-White, where you get these re-entry pathways, and this can cause life-threatening tachycardias. And very often cardiologists will ablate additional conducting pathways because they can cause problems. So we see that the AV bundle is directly continuous with the AV node, and then the atrioventricular bundle continues and it divides into the right bundle branch and it divides into the left bundle branch. Again, this specialised conducting tissue made up of specialised myocardial cells, specialised myocytes. Now, the right bundle branch and the left bundle branch actually break down into other largish fibres that are going to take the electrical impulse to different parts of the ventricular myocardium. And these are called radiations. So these are radiations of the right and left bundle branch. So we can see here radiations of the left bundle branch. So on this side we see radiations of the left bundle branch. On this side we see radiations of the right bundle branch. And what this tissue is trying to do is carry the impulse down quickly through the septum and through the parts of the right and the left ventricular myocardium down towards the cardiac apex. Because the whole aim is to get the apex to contract first. So the impulse is transmitted rapidly down here towards the cardiac apex and through these other radiations. So the heart will contract from the bottom up the way. Because what we want is for the heart to contract up like that, starting at the bottom. Because we want to get the blood, of course, to the arterial valves which are here. So if we started contracting at the top, that will push the blood from there down there, which would be completely useless. So we need to start from the apex going up, so the contraction channels the blood towards the arterial valves to be discharged into the systemic circulation and to be discharged into the pulmonary circulation. And then these radiations eventually break down into smaller fibres. And these smaller fibres here, which actually take the electrical impulse into the ventricular myocardium itself, these smaller fibres are called the Purkinje fibres. Now, they actually do have relatively large diameters considering they're microscopic fibres, and the impulse is transmitted rapidly. So we get innervation of the ventricular myocardium starting at the apex and working up the way. So the heart will contract in like this, and at the same time impulses will go back up here through the Purkinje fibres into the septum itself, causing the septum to shorten. So the ventricles are going to go in, the septum is going to shorten, so the heart is going to contract in like this and up the way like that. And there's actually something else called ventricular twist as well, left ventricular twist. So during systole, what actually happens is, it's a bit complicated, but the base moves that way and the apex moves that way. So the base moves that way and the apex moves that way. And what this does is it kind of twists the heart as well. It's a bit like wringing out your washing. So it's going to contract in the way, up the way, and it's also going to twist in that direction. The heart's going to twist in that direction as well. And that helps the ejection of blood from the ventricles. And as well as that, the twist stores potential energy. So the heart's going to twist in that direction, and then when it relaxes at the end of systole, it goes back the way, and that helps to suck blood in as well from the atria and from in this case from the pulmonary veins on this side, to promote ventricular refilling. It's interesting, Christian Barnard, who did the first heart transplant in 1967, didn't actually know about cardiac twist, and part of the reason that particular procedure wasn't very successful is he connected the heart in such a way that ventricular or cardiac twist didn't occur, so it reduced the pumping efficiency of the heart. So ventricular twist is also aiding the ejection of blood from the ventricles during systole. And of course, as the Purkinje fibres take the action potential into the ventricular myocardial cells, into the ventricular myocytes, each ventricular myocyte will change from being polarized to being depolarized. When it becomes depolarized, that's the message to contract. So that's how it contracts. So it's all done in this coordinated way. The impulse generated in the sinoatrial node causing atrial contraction, the blood going down from the atria to the ventricles. But then the collecting node, the AV node, the atrioventricular node, collecting the impulse, slowing it down, taking it down through the AV bundle into the right bundle branch and the left bundle branch, through these radiating branches into the Purkinje fibres, coordinating the contraction of the ventricular myocardium. So all of the ventricular myocardium fibres are contracting in a coordinated way, but basically starting from the apex, contracting up the way to pump the blood up towards the arterial valves. So while the heart is influenced by outside factors from the nervous system and the endocrine system, this autorhythmic arrangement of fibres allows it to contract completely independently of the rest of the body. Now actually, all of the parts of the conducting system, this electrical conducting system, are autorhythmic to some extent. So it's just that the pacemaker here, the sinoatrial node, is the fastest. It generates the action potentials fastest. It depolarizes quicker. So that's why it controls the impulse. That's why it controls the contraction of the heart, because it generates the impulses more quickly. But if there's a problem with the sinoatrial node, then the atrioventricular node will take over, albeit at a slightly slower pace. So this is the pacemaker because it generates the impulses more quickly than other autorhythmic tissues in the heart.